Okay, hello everyone. My name is Dominic, and today, as Mr. Bain said, I'll be giving a talk about my experiences at CERN during the summer. So, this year I was very fortunate to be selected for an internship at CERN. This picture here is Building 40. It's right beside the hostel which I stayed, which I'll show later in the presentation. In total, 280 students from 80 countries were chosen. These 280 were separated into two groups, member states and non-member states. Member states being from countries like, well, mostly European countries, so the UK, Poland, Spain, Portugal, Germany, so on and so forth, and non-member states being everyone else from the world. So there's me right there in the far left in the blue. I'm one of the few people actually visible in the picture. So a bit of background on CERN and the motivation for this talk. The Large Hadron Collider is the world's largest and most powerful particle accelerator, as many of you may already know. It consists of a 27-kilometer ring of superconducting magnets with a number of accelerating structures to boost energy on particles along the way. And CERN has gotten a lot of recognition since 2013 when the Higgs boson was first discovered, and the Large Hadron Collider got a lot of, notice, worldwide recognition from that. So a bit more about the Large Hadron Collider experiment is that it comprised of 7 experiments. CMS, ATLAS, ALICE, and LHCb are the 4 major experiments, and each of them serves their own fundamental purpose. I worked at CMS. That's actually not the real detector right there behind me. That's just a mock-up that they have at CMS. What happened was that in the summer, a Large Hadron Collider was on, so I couldn't actually go downstairs and view it. But the mock-up is good enough to fool people into making them think I was actually there. So, so each of them serves their own purpose. I worked at CMS, which is the compact muon solenoid. And this is how the front looks. Again, I wasn't actually here for the majority of the time. This was just a visit. I worked in an office far away since most of my work was about building a prototype, and I didn't actually need to be physically inside the building. So most of the people who work there are usually permanent staff members or more serious interns, such as PhD students or postdocs. Well, they're not interns per se, they're PhD students or postdocs, they're active researchers. So my project entailed building a working prototype for control and debugging of hardware that was to be used in future experiments. So working prototype here means a Junga web application. And what's my motivation for doing this? Well, as some of you may not know, the Large Hadron Collider is currently undergoing upgrades for new high luminosity collisions to probe for new physics. And this means that many subsystems of the 4 major experiments need upgrading as well. So many subsystems of CMS require upgrading, and they're using the LHC shutdowns as an opportunity to improve the performance of these detectors. So the upgrades themselves have served to highlight the need to attack problems that were previously unaddressed. And one such problem is the need for a tool that allows users to easily monitor, debug, and test for custom hardware. So mainly my project was as more of a firmware engineer interested in data acquisition. And data acquisition literally means just networking, because almost all of data acquisition requires a thorough understanding of networking in order to do it well. So the current CMS upgrades involve the use of a powerful processing card, which is called the CTP7. The CTP7 is the red card in the crate. The crate itself is called the micro TCA. So the CTP7 stands for calorimeter trigger processor card. And I'm going to break that down as to what that means. So what's a trigger? Is probably the simplest way to start attacking this. Within the LHC, bunches of particles collide up to 40 million times per second. So a trigger system saves only the potentially interesting events. And this reduces the number recorded from 1 billion to 100 per second. In essence, what happens is that there's actually 40 terabytes of information per second based on the particle collisions. And obviously that's way too much data to be saved in one or many systems, right? That's a lot of data. the handle. So you need they developed a trigger system in which interesting events can be identified. So you can think of a trigger system as a type of camera, where it does take images of the collisions, and then it picks which collisions are interesting, as opposed to which collisions aren't interesting. So you can think of it like many times when it's usually proton-proton. There's many different types of collisions, but I'm talking about proton-proton collisions right now. So proton-proton collisions usually, most of the time, result in a large number of uninteresting events, meaning events that we already have a lot of information about already. So the trigger system here is supposed to identify which events are uninteresting and then just remove them. And then the events that are interesting get saved to a tape, and then after those tapes get analyzed by the respective experimental physicists at CERN. So what's a calorimeter? Well, the CMS detector has two calorimeters. There's the electromagnetic calorimeter and the hadronic calorimeter. So the electromagnetic calorimeter is one which measures energies of particles that interact via electromagnetic interaction. And the hadronic calorimeter is one to measure particles that interact via the strong nuclear force. So here's a mock-up of the CMS slice. You see in the bottom left-hand corner of the picture, that's how the CMS looks, or if you were to be facing the detector itself. So you see that you can see the hadronic calorimeter in front of the electromagnetic calorimeter, and the keys give you the various particles which would pass through the detector. Since this is not a conference on particle physics, I don't think I should go further into describing these events. I'm just going to mainly say that you can see that many of the interesting things happen in the hadronic calorimeter. The hadronic calorimeter is the yellowish part of the image. So this is how big a solenoid slice is. You can see 4 people are in the solenoid slice, and it's pretty huge. And it has a very strong magnetic field. It's over 1,000 times stronger than the magnetic field of the Earth, and weighs the total of 12,000 tons, which is the highest energy magnet ever built. So the wire is super cooled. It becomes a superconducting wire, and the electricity we know that. Well, I know that if a wire is super cooled, it can, to pass absolute zero, then the electricity can flow without resistance, right? So why is CTP7 useful? So remember the CTP7 was this here, the red processor card in the micro TCA crate. So CTP7 is a powerful tool that uses the Vertex 7 FPGA, a field programmable gate array, as a primary data processor. It's a custom-made hardware between collaborations between CERN and the University of Wisconsin-Madison, which is the research group that I was placed in, the University of Wisconsin-Madison research group. It has Linux running on it, and it usually provides communication via TCP/IP and has onboard support functions. So there are plans for CTP7s to be used in the future CMS projects, as well as it's being used in research and development. So this is actually at the CMS detector. This is the backend. The CMS detector usually you can classify it into 3 different parts: the front end, the back end, and the computing farm. So the front end is mostly the sensors themselves, which would pick up the interesting data. The back end is more the hardware that processes this data, and the computing farm is more the horsepower that gets everything running, if you want to have that type of simplification. So this is you can see many CTP7 cards being encased right here in the micro TCA. And this is how it actually looks. Like there's many of these, you have these cabinets of sorts where you have different micro TCAs and other types of hardware being placed. And they're actively collecting data. Well, they were in this summer. So my methodology was to create a working Junga web application that will interface with the hardware, such that it can be used for the new high luminosity collision upgrades of the LHC. So the application connects with the CTP7 and receives data from the sensors in an asynchronous distributed manner. You'll remember from Mark's talk, he mentioned Celery, and Celery was also used here to receive the data in an asynchronous manner. It's a very useful library. It's a very useful Python library to get that job done. The web application also should be capable of adding new hardware and loading and adding registers, and as well as plotting relevant graphs from the data, read from the sensors, and triggering alarms in case of issues. So for instance, because I want to do things in, say, a distributed manner, the graphing library I used was Bokeh. So Bokeh is actually both a really, in terms of the aesthetics, it looks really nice, and it also gets the job done. That it has a lot of capabilities that very few Pythonic libraries have, such as it's able to add the data in real time. So for instance, the moment I'm getting data from the sensors, I can immediately update the graphs, and I can save snapshots of how the graph looks at certain points, or somewhat freeze the graph and then use the graph at a later point to see how it evolves over some time with the new data. So this is a small diagram showing how all of this was put together. So the control PC is connected to our database, and we communicated with the micro TCA, which hosted the CTP7s themselves. And the Junga, everything was done through RPC, remote procedure control side. It was not necessary for us to actually know any particular, it could be more or less language agnostic in terms of how everything is done, since we use RPC. MPEEK and MPOKE are Python methods. Since this was a prototype, MPEEK and MPOKE were like the prototype Pythonic methods, which we used to add registers, and like for instance, if we wanted the type of data we wanted, MPEEK and MPOKE could handle them. So for instance, if we wanted to change a value, in this case, it was a very simplistic example, such as a light sensor. If we wanted to change the color of a light sensor, we could use MPOKE and change the register value at that time such that the light sensor would have been different. If we wanted to get the temperature of a sensor at a certain point, we could have used MPEEK, and it would have returned the value of the temperature at that point. So everything over to the right-hand side of the diagram is more or less self-explanatory. It's the at some point I wanted to create a language agnostic description of the hardware via XML, but I never got a chance to do that. And there'd be a timer as well. So as I mentioned previously, if you want to see how the graph evolves over time, the timer would be useful here. So this is some code. This is an MPEEK code. Excuse me if it's a bit unrefined. So it's more or less, if you've done some networking, it's pretty straightforward. So what I'm basically trying to do is that as I get all the data from the CTP7 cards, I want to create a function that immediately returns what happens that immediately reads the value of the particular data that I want. So the data can be categorized into different aspects, such as temperature, light coloring, etc., so on and so forth. And I wanted to create functions in which I could access these particular attributes. So everything, because all this was done through TCP/IP, I used some networking, and I created some functions which could do this stuff. This is MPEEK, more or less, and this is MPOKE. So specific features, as I mentioned earlier, I wanted to integrate the Celery library to manage the data received from the sensors in a distributed asynchronous manner. And I wanted to use the Bokeh library to produce real-time plots from the asynchronous data read from the sensors. And I wanted to implement a function that would trigger alarms in case of any faulty hardware. Again, Celery is also very useful here, because what happens is that if there's any fault with, say, a CTP7 card, you don't want it to immediately halt all the processes and focus on that only. You want it to still read the data from the other cards and then tell you that something is wrong with one of these cards, while everything else is still performing well. So Celery is also very good at doing that in terms of creating jobs and tasks that can do things in a distributed way, that don't rely on other functions that don't do things sequentially. So I wanted to create a language. I also wanted to implement a language description of the hardware with XML. I didn't get to do this. Here's my future plans. One aspect I didn't address during the duration of the project was support for CERN-made protocols. So most boards at CERN use the protocol called IP bus. which is a simple, reliable networking protocol for serialized data. But in more recent time, there's a shift to more standard protocols, such as Google protobuffers. And an interesting side project to do would be exploring the possibility of support for IP bus during future development plans. So this is a example of the web app running. You can see I'm not big on design. Okay, but our written report can be found here, and my video presentation can be found here as well. But wait, there's more. Yes. I also entered CERN WebFest during my stay, which is a hackathon at CERN. And these are the slides. I entered it with 2 other summer students. So I entered with Philip Hackstock and David Werst. Philip is from Austria and David is from Germany. So our idea was to create a web application, also using Junga as well, that would take papers from arXiv and allow them to become much more tractable to both young and old, and more experienced researchers alike. So why arXiv? Well, it's a big preprint platform. I mean, everybody who's into research knows arXiv. It has a huge community. It's moderated when you have papers being put in there. It's free access. But the problem is that it's not very accessible to outsiders. Unless you're an active researcher in a particular field, it's not a very useful site for you, unless you want to spend a lot of hours trying to figure out what the author is saying. So our solution was to provide a platform for authors and community, for the authors and community. So make cutting edge science less intimidating for students and researchers from different fields. So the idea was to mix arXiv with Wikipedia with GitHub. The basic functionality, it should combine those 3 functionalities. It should have the functionality of arXiv, it should have the functionality of GitHub, it should have the functionality of Wikipedia. All right, what does that mean? It means that you should be able to have a document, and it does something similar to what, you know that site, Medium, the blogging site, where you can highlight comments, for instance, and then you can highlight sections of the article and make comments or whatever. If arXiv had that similar feature, then it would be really useful, because usually what happens is when you get a research paper, you end up underlining things and you end up trying to read things and make sense of stuff. But the moment you do that and you understand stuff, it's only local to you. Anyone else who's going to read that paper is not going to have all that stuff that you did, all those notes that you jotted down and all those things that you underlined. So we wanted to create this type of community like GitHub, in which you would get an arXiv paper, the text would be scraped and then reformatted using MathJax and via MathJax and HTML, and it would allow users to edit the arXiv document itself and send pull requests to the author. And we wanted it to be free, like Wikipedia. Like anyone can go on Wikipedia and search for a document. So if you wanted to search for a certain keyword, here are certain keywords that come up within Wikipedia that give you some information about it. So the general idea is to provide a platform for simplified summaries. So originally our idea was for simplified summaries, and that is still the idea. But we wanted to expand it more than that. We wanted to say, have a simplified summary, but be able to annotate the original paper, so we can see where the summary came from. Many researchers often annotate papers, I mentioned that already, and it makes really complicated ideas really accessible to them. However, it only remains accessible to only them. So let's make it accessible for everyone. So the feature it should be able to browse the latest results in science, a website that provides well-readable summaries for the broad community, interactivity for and communication between users and authors, so on and so forth. So here's a short example that we had presented in the WebFest. So it was, this was very simplified because we only had 2 days to make this. So we didn't actually get to go on and implement everything that we had planned to implement from the get-go. But this is the best we could have come up with at the time. So for instance, gravitation, if you're not familiar with what that term is in a physical sense, you could always click on it and then it would take you to a page in which you get relevant articles and you get relevant annotations and a summary, and a somewhat accessible summary of what gravitation is. And here's a comment feature underneath. Whereas I ideally identified the comment feature should be within the article itself. As I said, that involves a lot of JavaScript and a lot of headache. So that wasn't, I mean, this project is not dead. We just haven't had the time to work on it completely yet. But it did get a lot of praise at CERN, and we were encouraged to continue working on it. So I thought it was worth mentioning here. So for instance, this is what I wanted to do. Like you could hover over a highlighted aspect of the article, and you could be able to, for instance, tweet a particular aspect of it or annotate something, so you could further you could read a further exposition on what the article is saying. So right here, for instance, you could click on the highlighted version and then see what someone else is saying about this their paper. The plans was to integrate a library to rip text from the PDF files and allow the users to customize the rip data with comments, allow users to see comments when they hover over a commented region, and users can push comments to the original document and have the author approve them, then incorporate them into the original document. So this was us. My CERN email still works, by the way, so you can contact me. Contact me there. This basically ends my talk. This is my other contact information. I have some random pictures because people generally ask me what's it like to work at CERN and what they want to have an idea of what it looks like inside. So this is at LHCb, the Large Hadron Collider Beauty. That's me right there looking at the camera. This is the computing center. Not the computing center. This is in the CMS. Notice everyone at CERN has at least 6 monitors around them at any given time. This is one of the first 2 web servers in the world.
That's a keyboard.
No, this is the keyboard connected to one of the first 2 web servers in the world. I couldn't get, the title and the computer in the same shot, so I had to stick for the title and the keyboard. Okay, this is the antimatter factory, where they make antimatter, amongst other things. That's classified. This is the linear accelerator. It's very interesting that the starting point for all the experiments is this hydrogen canister. That pretty much these huge accelerators start from just this hydrogen canister alone, where they get all the protons from, and they're accelerated through these massive structures. This small canister here, which you could probably lift, is the starting point of many new physics, a lot of new physics. This is Elna. I don't remember exactly where this is, but it was in CERN. And this is Alice. You can see how huge it is because you can see 2 people standing right here. Comparatively, the size of this man and woman compared to the size of the detector itself. So you can see it's a really huge detector. And this is where I lived. This is building 38. Yeah, and that's the end of my slides. I should have probably put questions here, but I'm accepting questions now. Bokeh, I looked at all the Python libraries via Google, and I fell in love with Bokeh. I mean, in terms of personal preference, I don't think there's any, well, to me personally, I don't think there's any graphical library, Pythonic graphical library better than Bokeh right now, in terms of data visualization for my particular purposes.
Is there none that what? No Python libraries that what?
That are better than Bokeh.
Okay. Cool. No, I don't know any. So he's certainly the one that I'm going to use.
So any more questions?
I probably missed it, but what does CERN mean?
It stands for the European Organization for Nuclear Research in English. In French, I have no idea.
Central Europe.
Okay, I take advantage of this lull.